Hi everyone, welcome back. Happy New Year, happy holidays, all of those. Welcome back. We're going to start off with some intro to polynomials. This is chapter 4. So we did chapter 5, now we're moving backwards. I'm going to start off with some vocabulary. This might be a good place to stop so you can copy this down and then press play again. The first word we're going to be introducing is the word polynomial. So polynomial is a monomial or a sum of monomials and one or more variables. So that's something like, if you see this example, we have negative 2x squared plus 3x minus 4. And we've seen those. Those are our quadratic, what we've been using to graph our parabolas. And that's just called a polynomial. It could be 1, 2, 3 terms, or it can be 2 terms, as you see down here, or it can be more, like you see in this one down here. We're going to be focusing on working in standard form of a polynomial. That means that when you write it, your exponents are in order from the largest to the smallest. So in this one, you see that we have a 2, we have a 1, and then we don't have a variable at all. So you want to put it from the biggest to the smallest. The standard form is this one, and I know that the n's look a little bit weird, and then there's like n minus 1. That just means that the n is the biggest number because everything as you move down, you're subtracting. So when you subtract, it's getting smaller. Until ultimately you have something that doesn't even have a variable. That's called our constant. It's our number. So if you look at this here, you have a number that minus 4, or if you remember when we were factoring, that's our c value. That doesn't usually have, so if it's a constant, that means it doesn't have a variable. In this example, we have a quadratic. We would have that parabola because the exponent of 2, that is called our degree. Once you write it in standard form, that largest exponent, that very first one, tells us our degree. So since it's a 2, it's a quadratic. We know it's a trinomial because we have 1, 2, 3 terms, which makes it a trinomial. And once you have it in that standard form, the number at the very front, our coefficient, is called our leading coefficient. So that would be a leading coefficient of negative 2. We are also going to be talking about the end behavior of a graph. So that kind of goes back to whether it opens up or down, the direction in which you would draw those arrows of your graph. We're going to be focusing as the x. So looking at a graph going left to right, as those x are going to a positive infinity, meaning as they move this way, or they go negative infinity, meaning they go to the left. We're going to be naming these polynomials. So if you see right here, I named this a quadratic trinomial, and I color-coded it because the degree will tell us what that first name is, which is a quadratic. The number of terms in pink is that second name, which is our trinomial. So for example, when you have a degree of 0, you have a constant. That means that you don't have a variable at all. That is like this negative 4. If I didn't have anything other than that negative 4, that would be a constant. You have a linear when you have a variable with an exponent of 1. That would be like this 3. Your exponent is 1, which makes it a linear. You have a quadratic when you have an exponent of 2, and here I did it in that purple so it can match. 3 is a cubic, meaning that the exponent is a 3. 4 is considered a quartic, meaning the exponent is 4. Now, these two get a little bit confusing because qua kind of makes us think of quarters, which is a 4. A quadratic, however, is a 2. And a quartic is a 4. So just keep that in mind. And these do keep going, a quintic and so on. But these are the ones I want to focus on here. We're also going to be naming them based on the number of terms. So in this one, like I said, I have 1, 2, 3 terms. So this is a trinomial. When you have one term, you have a monomial. And the prefix of that word is mono, which means 1. When you have 2, you have the prefix of bi, which means 2, and you have 1 and 2 terms. 3 is a trinomial, 1, 2, 3 terms. Anything that is 4 or greater, you use that number term polynomial. So for example, I have 1, 2, 3, 4. This is a 4-term polynomial, meaning it has 4 terms. I want to distinguish between these two. So say, for example, this one here. The degree is a 5. So that you would go on this side, find the name, so it would be a quintic, which isn't here, but it would be a quintic, and then the number of terms is the second part. So you're looking at 2 different things. You're looking at the exponent, and then separately, you're looking at the number of terms. So in this one here, we had a 2, so the quadratic. In this example, I have 3, and in this example, I have 2. This is a quadratic 1, 2, 3 trinomial, where this one is a quadratic 1, 2 binomial. So make sure that you know that it's 2 different things that you're looking at here. So we're going to go ahead and get started with our first practice problem. I want us to write each of these polynomials, there's going to be 2, in standard form first, and then I want you to name it by degree and number of terms. So let's get started here. The first thing I want to do is I want to identify that biggest exponent, because I know that to write it in standard form, I need to do it from largest to smallest. So I have a 2, I have a 1, right? If you don't see it, then you know it's a 1. I have a 3, and I have a 5. Now this one doesn't have it, so that's going to be a 0, because it doesn't even have the variable. And remember that that would be a constant. So the biggest one I see here between the 2, the 1, the 3, and the 5 is that 5. So that would be my first term. So I'm going to say that, in standard form, this is going to be 6x to the power of 5. I forgot my f of x. So I use that one. I'm just going to cross it out so I don't get confused. The next biggest one is this 3, so I'm going to take this whole term. Minus 4x to the power of 3. I'm going to go ahead and cross that out. I'm looking at the 2 and the 1, so I'm going to take that 2 plus 1/2 x squared. Go ahead and cross that out. Plus 3x. And you can write the exponent of 1 if you want to. I'm not going to. And then lastly, minus 1. So this here gives me my equation in standard form. So I checked that part off. Now I want to name it using degree and terms. So my degree is determined by my exponent. So I am going to find the biggest one, which is a 5. Now it's not on here, but it's going to be a quintic. And then the second name is going to be determined by how many terms I have. So here I have 1, 2, 3, 4, 5. So since it doesn't have a specific name, I'm going to say it's a quintic 5-term polynomial. And that gives me exactly what I am looking for. It gives me my equation in standard form, and it gives me my name. So let's look at a second example. Let's look at f of x is equal to 8x cubed plus 7x to the power of 4 minus 9x minus 3x squared plus 11. I want to start off by identifying all of my exponents. Now for standard form, I have my f of x. I'm going to start off with the biggest one. So I have 3, 4, 1, 2, 0. start off with my 4. 7x to the power of 4 plus 11. Okay, now I'm not quite done yet. Now that I have it in standard form, I can find my degree, which is my largest exponent. I look at my table, so my exponent is a 4, that degree. So this would be a quartic. And now I'm going to count my terms. I have 1, 2, 3, 4, 5 again. So it's a quartic 5-term polynomial. And that's it. Okay, the next part of this is evaluating. So we're going to evaluate the polynomial at the given x. We have an equation and we have a value of x. That means we're going to substitute it in. This is going to be helpful when we start solving to create tables and to graph. So we know that x is equal to -2. So for every x that I see in my equation, I'm going to substitute it with -2. So I'm going to say f of x minus 3x to the power of 4 plus 2x cubed minus 12x minus 6. And in place of all of those x's, I am going to substitute it with this x is equal to -2 here. Like this. Okay. So you want to make sure that you solve this part first. Remember, you always do exponents before multiplication. So I'm going to bring down this -3 for now. And I'm going to multiply that by -2 to the power of 4. So that's -2 times -2, which is +4. -2 times -2 is a +4. So +4 and +4 gives me a +16 plus 2 times -2 cubed. So -2 times -2 is +4 times -2 is a -8. A negative and a negative will give me a positive. 12 times 2 is 24 minus 6. Okay. 3 times 16 is -48. Minus 2 times 8 is 16. Plus 24 minus 6. So I'm going to keep doing the math here until I get my final answer. Okay, so this would give me 64 plus 24 minus 6, -40 minus 6, -46. So f of -2 is equal to -46 would be my final answer. So again, what I did here was I was given a value for x. I substituted it into my x values. I evaluated all the way until the end and I got -46. So we're going to try one more. All right, here we go. So we have a cubic because the exponent is a 3. 1, 2, 3. Trinomial because we have 3 terms. I am going to substitute all of my x's with this value here. So we get f of x is equal to -5x cubed plus 2x squared minus 11, where I substitute in those parentheses a 3. So again, I want to make sure that I do my exponent first. So 3 to the power of 3 is 3 times 3 is 9, times 3 is 27. 3 squared is 3 times 3, which is 9. Negative 5 times 27 is negative 135 plus 18 minus 11. Keep going to get my final answer of 128. That means that f of 3 is equal to 128. Okay, so to talk about end behavior, we have to talk about the shape of a graph. When you have an equation, you could either have an even degree or an odd degree. An even degree would be something like, say, x squared, or, 3x to the power of 6. I'm only looking at the exponent itself. To have an odd degree, it's something like x to the power of 1, or x to the power of 17. The only thing that I'm worried about here is whether that number is even and odd, because that's going to help me determine my end behavior. Now you see that these are arrows. They kind of look, I don't know, like smiley faces almost with this one, but they are the arrows of my graph. So say, for example, I were to graph this one, x squared. I know that my graph could either look like this or like this, whether it's opening up or down. If this was x to the power of 1, this could go like a line like this or a down line like that. An overgeneralization, and I mean this is very general, overall, exaggerated simplification. Like, I'm not saying it's going to look exactly like this, but if I were to graph this here, the general shape of my graph would be the same way. Now for the odd ones, we don't do straight lines. The general one we're going to use is actually a little curve like this. We call this would be the graph to a cubic function, but we just use these as a main idea. We only care about the arrows at the end. We don't care about what's on the inside. The only way to get from here to here is something shaped like that. The reason we care about these is because we're going to turn these into a small table that's going to help us find the end behavior with nothing but the equation. So you guys know I like my area model, so I'm going to go ahead and use that with this. And this is going to be like a little cheat code. There's 4 things we want to identify in an equation. The first is whether that degree is going to be even or odd. So here I'm going to put an E for even, an O for odd. The second thing we care about is whether this is going to open up or down. And the thing that determines that is the sign. So if it opens up, that means it's a positive. If it opens down, that means it's a negative. So when you have something that is even, so one of these, and it's positive, you'll have something like this. Now remember, we only care about the arrows at the end. If it's negative, we have like this. If it's odd, it goes like this, and if it's a negative and an odd, it goes like this. So this is going to be our cheat sheet. It's going to tell us our end behavior, where those arrows are pointing at the end. Okay, so let's look at our first example here. 6x to the 5th minus 4x cubed plus 1/2 x squared plus 3x minus 1. If this looks familiar, it's the first example that we did when we wrote it in standard form. The only piece of information that I need to take from this entire equation, once I make sure it's in standard form, I care about this and this alone. This tells me my leading coefficient, which is what I need to know whether it's going to be positive or negative. And I need my degree because that's going to tell me again whether it's even or odd. So in this one, I see it's even. it's a positive, right? So it's going to be one of these two. And then I look at my exponent, which is a 5, which is odd. So in the positive, I'm going to go to the odd, and I know that my graph will look something like that one there. So again, I'm looking at just the first term. I want to know whether that leading coefficient is positive or negative. That would tell me which side to go on of this line. Then I want to look at the exponent, and I want to know whether it's even or odd. That's the easy part. From here, I just want to know what happens as x goes to positive infinity or negative infinity. So I'm just drawing this here as like a guide. It's not really there. But as my x's are going to the positive infinity, what is happening to that arrow? Is it going towards, so as x heads onto positive infinity, what is happening to my arrow, to my actual equation? Where is that going? Is it going to positive infinity or is it going to negative infinity? Well, that arrow is going up towards positive infinity. So that means that as x approaches positive infinity on this side, my f of x, my equation, goes to positive infinity as well. Then I can do the same thing with this one here, because this is my negative infinity. So as my x approaches negative infinity, what happens to my actual graph? Well, that one also goes to negative infinity. I'm kind of telling the direction of it. So let's look at this next one. Again, I only care about this one here. Again, it's positive. It's a positive 7, so I'm going to be looking at this, and it's a 4. So it's even. So I'm looking at this shape here. So in this graph, as I'm moving in the direction of positive infinity, what happens to my arrow? So as these are my x values, as that goes to positive infinity, where does f of x go? Does it go to positive infinity or does it go to negative infinity? It goes towards positive infinity. I'm sorry. Now, as x approaches negative infinity, meaning it goes on the left side of it, my graph still goes to positive infinity. So in this one, you notice that as it goes to positive, it goes to positive, and as it goes to negative, it goes to negative. But in this one, it still goes positive to positive, but as we go to the left, towards negative infinity, my graph is still staying at positive. That means that my arrows are always going towards positive infinity, whereas this one on the right, because that's a positive, it's going to go up, and on the left, it's going to go down. I guess I can write like the left here and the right. This is going to go up, and this would go down, which kind of describes exactly what's happening in my graph here. Again, as this one goes to the right, my graph goes up, and as it goes to the left, it still goes up. Okay, so for this one, I rewrote my graph, my little table chart right here so I can reference it. I only care about this term here. The negative is going to tell me that I'm going to be on this side, and the 4 tells me it's even, so I'm going to do this one here. So my graph is going to look something like this. So again, as I'm looking at the right, so as my x, because this is x, left to right, approaches positive infinity, meaning it goes to the right, what happens to my graph? Well, it goes down. So f of x approaches, since it's going down, it would go to negative infinity. And as x approaches negative infinity, what we do on one side, so what we do on the right, we also have to do on the left. So this side, I'm going to write my left right there. F of x approaches, so my left arrow goes down as well, which is negative infinity. So on the right arrow, my graph is going down. On the right, my right arrow is facing down. On my left arrow, it is also going down. And our last one is going to be this one. So again, I only care about this. I don't care about anything other than this part here. So again, I have a negative, so I'm going to be looking at these two, and I have a 3, so I'm going to go to the negative, the odd, which takes me to this one here. Like this. So, as x approaches positive infinity, so my right arrow, f of x, approaches negative infinity, points down. And as x approaches negative infinity, meaning the left, f of x approaches, so my left arrow, positive infinity. And that is it. So for more reference, I would say in your book, you can go to section 4.1 for additional practice or examples. Toodles!